when I started streaming. Can you hear me? Okay, thank you, Samantha. Okay, I'm going to start because we have a long lecture today. The lecture today is about algorithms, but before I dive into the lecture, I just wanted to have just a little word about the network project that is going on. I know that most of you submitted your home network project on Sunday or Monday. That's great. I've been kind of watching, see how the routers, the street routers are coming along. And so right now I'm in the south side auditorium. I see that Zone 1 has their zone router here, which is great. And fortunately, there's only one street who has put their routing information. So I hope that more streets on Zone 1 get their act together and start putting their routers or their router information here. So it was, I think it's Brian Trin who was kind enough to put the router here and put a sign on top saying what the coordinates are on Zone 1. This is great. So everybody can just drop their routing information on the router. I see that in Zone, let's see what's going on here in Zone 2. I think I've seen a router also here in Zone 2 somewhere. Let me see. Yeah, there you go. So I saw the router over here. This is the Zone 2 router, and it already has 3 entries, which is great. So Zone 2 is winning. And hopefully, you guys today can organize yourselves and finish connecting everything. I think I saw a message on Piazza about the backbone of the south side being, I think, in coordinate 00, I believe. So make sure that you connect this guy at least to coordinate 00, wherever the backbone router is. Let me see where this is connected. This one, that's right. So the upstream is 0023. So it seems to be the backbone. So 0023 is the backbone of the south side. I've been looking at, yesterday I went to the north side and I saw, the home networks, but I didn't see the zone routers yet. So the south side is ahead of the north side. So please catch up. Hopefully, very soon, today or tomorrow, and certainly during the weekend, I want to see messages flowing all around, okay? Including from the different continents on this virtual world. All right, are there any questions that I should address before I start the lecture on algorithms? Okay, so if there are no questions, let's dive in. I just have, okay, I have one remark, just one remark. The peer reviews for the network project are going to be assigned only on Monday. So I'm waiting for the entire network to be configured, and then I will assign peers, and what the peers are going to test is if they are capable of sending messages from their home terminals into the peers terminals, okay? So that is going to be the peer review. So, but we need to have the entire virtual internet connected in order for this to work. So if you don't see if you don't see your peer reviews assignments yet, it's because they haven't been done. So Arkin has a question. How many screenshots do each turn for the street router assignments? So I think it should be 2 screenshots per house. So I want one screenshot that shows that you are capable of sending a message to another neighbor of your street, and I want a screenshot that shows that somebody in your street is capable of sending messages to you. So everybody in the street should have 2 screenshots. All right, another question. How do we get the member of on my name tag? Right, so you have to select a group. You have to sign up for the groups. Hopefully you signed up for the right group. And then if you do click on your avatar, and then you select you create groups, not on my hair, on your avatar, and then there's a groups option over here, and then you can activate. So select which group you want. For example, I'm going to say builders, and then activate. All right, and then you will see your role inside the, on top of your head. Okay, Twitch stream link. Thank you, Nicole, for saying that. That's very nice. Noel has another question. So would it be around 16 shots for the messages only? Streets, yeah, 16 shots for the street groups. That's right. If you have 8 people on your street, there's only like 1 or 2 streets who are actually full. All the other streets have slightly less people. But yes, if you have 8 people on your street, that would be 16 shots. All right. Any other questions? One more question, Nicole. What if there are some neighbors who haven't reached out to the rest of the street? Some people have been having real life problems, and they have sort of kind of silently dropped. Some of them send me an email. So if you don't hear from your neighbors, just assume that they are incapable of doing the homework, and just proceed with whoever is in your group. Just move ahead. Don't wait. Okay? All right, so having said that, let me move on. The network project, I think, since you guys were able to connect your home routers, the other routers is pretty much the same. So there's not a lot of difficulty in connecting the whole thing. So I hope that you will be able to connect everything quickly, and then we'll be able to send messages around. Okay, Peter has another question. Some of my neighbors have not done the first project. Oh my God. Okay, well, if they don't do the first project, you just have to assume that they are, incapable of doing the homework project. I know that there are some people who are really having real life problems, and they are incapable of participating in the class. So it may be the case of some of your neighbors. So just assume if they don't contact you. I think you guys have been, some of you have been doing a really nice job at trying to connect and sending messages on Slack and on Discord and all that. So that's it's best that you can do. If the other people don't connect to you, it's because they're really having some problems and they're not participating in the class any longer. All right. So having said that, let's move on. So since the network project is going well, I'm going to move on to the next block of lectures in this course, which is the lectures about algorithms. This is sort of something that is very central to computer science. And it's very weird in the beginning when you start learning about these things, like almost feels like kids plays, some kids charades, a lot of puzzles and a lot of little details, and in fact, well, that's sort of what it is. Not completely untrue. So I'm going to talk about algorithms, introduce you to algorithms today. I'm going to show some live algorithms in action here. There is already the next project that you are going to do on algorithms already posted. You have until like the end of next week to do it. I know that algorithms are always a difficult thing. So I'm expecting that you guys will keep the TAs and myself busy next week with office hours and and all of that. Okay, so having said that, let me move on. So let's revisit something that you all did already on project one, which was the max program. And I threw you at the max program and at the average program without a lot of guidance, right? I just told you what the machine could do. Here are the machine instructions. Here are some examples. Here are parts of the programs. Now it's up to you to kind of put them together and make it all work. And I know that it was super difficult. It is difficult. Okay, I wanted to have that first kind of emotional shock of like, what is going on in here? This is way too hard. And so having struggled with those, trying to put that program together, and I know that many of you spent a lot of hours sitting in front of the computing machine trying to figure it out, which is great, okay? Let me now kind of step back and try to teach you how to do these things. There's like a lot of other activities. The more you practice, the better you get at it, and that's certainly true with algorithms, with programming, with all that. It's practice makes a huge difference. But there is a little bit of knowledge I think that I can give you to kind of bootstrap that process of trying to wrap your head about if you are given a computational problem, how do you even start, right? Where do you even start? Because it seems everything is so complicated. So here's let's revisit the max, and then we'll reflect on what that means. So the max, for some of you who have come to my office hours and extra office hours, you probably saw that I always start with something that is not the complete solution. It's like, think of the simplest thing that could possibly work. Like, it's not the max yet, it's just something that is sort of related, but it's super simple, okay, that you can do in just a few lines of code. So for example, when we're doing the max, we want to find out the maximum of a set of numbers that are entered by the user. Let's just reduce the problem to just find out the maximum of two numbers. Okay, so we just accept two numbers and we compare which one is greater, and then the greatest one is the maximum, right? So we have something like this: read one input, read the second input, and then we test. If the second input is greater than the first input, then the maximum is the second input. Otherwise, the maximum is the first input. And then the maximum is in this max thing this concept of max that we have around, that's going to be important for. So this is the simplest possible thing that could work, right? But of course, the problem is more complicated than this. The problem is that we don't want just two numbers. We want many numbers, right? And so we need to somehow accept more numbers than just two. So let's patch what we have with more things. So we read one input. So when we can say, okay, so once we read one input, then by definition that is the maximum, right? We only have one input, that is the maximum by definition. So now we have the maximum gets the input one. And by the way, this left arrow means maximum gets I1. Okay, maximum gets the thing that was read from the user. Okay, so once we have this, then we need to go sort of on a repetition of accepting many inputs, right? So we go something like this. So we accept another input, and then we test. So this is the same thing, right, as before. We're still testing just two numbers. But now we're not testing I1 against I2. We're testing I2, which is this number that we are accepting next, against the maximum, right? And in the first time that we go here, the maximum happens to be I1. But since we are going to go sort of on a loop, the maximum is going to change, it may change. So we're going now to compare I2 not to I1, but to the maximum, right? So we compare if I2 is greater than the maximum, then we actually overwrite the maximum with the new value of I2. Otherwise, the maximum stays unchanged, right? So, and then if we go back again, do another iteration, you read another input, and again we test that third input or whatever against the current maximum, right? And we keep doing like that, and so now we have a mechanism to get the maximum of many numbers that are going to be inputted by the user, right? Now the problem with this version of the program is that it never ends, right? It just goes on here forever asking for input and comparing, finding whether the new input is maximum or not. So this is still not quite right. So, but we need to somehow have exit points out of here. So let's see what the requirement said with respect to that. In the spec said that you have to stop at 8 inputs. So after 8 inputs, you stop. The program stops and spits out the maximum. Okay, so now these are the lines in green, are the lines that I add to my program in order to be able to cope with this extra piece of a requirement. So how are we going to do this? The max 8 inputs can just, so Tom is saying the max 8 inputs can just be used from average. Yes, so exactly. So in the average program, you already had that mechanics of accepting 8 inputs from the user. That's right. So you could look at it. But let's just imagine that you're designing this from scratch. So how are we going to just accept 8 inputs? What that means is that we need to count. Somehow we need to count how many inputs are we on right now, right? So let's say that we have a counter, all right? And we initialize that counter to 8. We set it to 8. And now we go on our loop, right? We go on our loop. That was the loop that we just did, which is to read another input, test if you have to change the maximum or not. But once we are done with checking whether we have to change the maximum or not, then we have to do more things. We have to decrement the counter because we went through this once, right? So we have to decrement the counter, and then we have to test. If we reach 0, if the counter reached 0, then we get out of here, right? We move on. Otherwise, if it's not 0, we go back and to another, right? So this is the thing that allows us to do this only 8 times, right? So these are I'm starting to weave things here. As you can see, you started with the simple things that could work in black. Then we added handling multiple inputs in blue. And now I'm heading, stopping at exactly 8 inputs in green. All right. But we're not done yet because the requirement said something else. It said that if the user enters a 0, then we should stop. Okay, so that is still not here. Okay, fine. So let's do that. Okay, so where should we put that? Well, probably immediately after the user enters an input. So if it's 0, we just get out of here. We don't even do anything else. We don't test whether we are out of 8. We don't test anything. We just get out, right? And then in any case, the maximum is in max. All right. So basically, what I got to do is like start with the simplest thing that could work, that is not the entire program, and then start adding more, the things that make the program more complex. But start adding one by one, and make sure that you understand, what part of your program relates to that particular thing that you're adding. It's important to kind of keep it organized in your head. So in other words, what I just did here and what I just wrote here is what's called an algorithm. It's an algorithm for finding the maximum value in a set of up to 8 numbers. 8 numbers or fewer, right? It's an algorithm that does that. What is an algorithm? An algorithm is a step-by-step procedure to make the computer solve a problem. All right? It's sort of like a recipe, or for example, a standard operating procedure in a operating room, for example. Okay, so there are many fields, not just computer science, that have this concept of a set of steps, very precise steps that you need to do in order to achieve something. And so, this is called algorithm in computer science. So for example, the max accepts up to 8 numbers as input and produces the maximum of those numbers. And so, if we give this problem to a person, find out the maximum of these numbers, we immediately, zoom in immediately on the 9. Oh, it's 9, obviously, okay? But the computer doesn't quite know how to do it. The computer has no idea. We have to tell it. And we have to remember, the computer is a dumb machine. Remember Babbage's machine? So this is what you need to think about computers. It's like miniature Babbage machines. We need to tell it what to do, where to go, what to store where, when to go fetch this piece of thing in here, when to compare things. We need to tell it everything. So, there's a real difference between asking people to solve problems and asking computer to solve problems. So people rely heavily on our powerful sensing systems, right? We have our visual system is amazing, all right? It's really amazing. in the hearing system too. We rely, and moreover, we rely on past learning of concepts to infer new knowledge, right? We learned numbers in school. We learned the basic algebra in school. We can, figure out more or less what is it that we're being asked to do. Computers cannot do any of that. So the sensing capabilities are very limited. And the classical computers that I'm covering here in this course, there is no learning whatsoever. You have to specify everything. There are, newer models of computation where we start being able to kind of have a notion that of how to teach computer, how computers can learn from examples, but that's not what I'm covering in this course. It's what's called machine learning these days. But so what are the strengths and weaknesses? So people can solve difficult tasks very quickly, like recognizing faces, for example. It's a very difficult thing for computers to do, and it's something that for us is very easy. Or recognizing words or filling in the blanks, things that, words that are missing. We're very good at that, but computers are not good at that at all. But on the other hand, we cannot hold on to large sequences in memory. The maximum, the average that people can hold in memory is like 7 things. So if you need to sort out, I gave you on that problem, I gave you to sort out, 6 numbers, but if I had given you 6 million numbers, you would be, it would be difficult to sort 6 million numbers or find the maximum of 60 million numbers by hand. That would be very, very difficult. For computers, they don't care. Okay, so for computers, they can solve simple tasks very quickly on huge sequences. They don't really care about the size of the input. And once we find ways of solving problems and then break them down in precise steps, and we tell the computer, then the computer can reproduce those steps over any number of inputs, any size of inputs. It's great, right? We automated something that would take us a very long time to do. But once we figure out how to break it down in little steps, we put it in a program and the computer can do it. Okay, that's great. But again, a lot of the effort is on us. We need to figure out how to do things first, how to break it down in small steps. That's up to us. Unfortunately, it's still up to us. Unfortunately or fortunately, there will be lots of employment for computer scientists and software engineers for years to come, because this is still a very difficult thing to do. So what are simple computational problems? Are problems that are in computer science, in programming all the time. These are the bread and butter of programming and of computers and software. So sorting a collection of things, searching an item in a collection of things, things like in math, like matrix multiplication, finding square root of a number, finding the shortest path from A to B in a graph, visiting nodes in a tree, compressing text, all of this, okay, there needs to be algorithms for doing all of this, okay? So people have been, powering into computer science over the past 70 years to figure out, the most efficient algorithms to do all of this stuff. Because we need to tell the computers. But once we have an algorithm, once you have it broken down in a way that the computer can execute, then it's great, right? To just have that algorithm and the computer can just do it for us on any size of input, and it does amazing things. But still, the hard part is on us. So I'm going to cover now the process of creating algorithms. And this is what I know that many of you were struggling on project one, because you never were asked to do anything like that, right? You're asked like, write a program that computes the max. Right? It's like, where do I even start, right? So how to create algorithms is a funny thing. And again, there are 3 things actually involved in creating algorithms, not just one. And it's important to have these 3 things in separate, because they require different kinds of skills and require you to focus on different things. So the first thing is to understand what the problem is, okay? Understanding what the problem is absolutely fundamental. If you don't understand the problem, you may come up with an algorithm, but it will very likely be wrong. You have the right algorithm for the wrong problem, right? So understanding the problem is super important. And I will show you sort of what kinds of techniques and strategies you can do to really test yourself whether you really understand the problem. So what's the input output? What are the restrictions? What are all the constraints of my problem? So, and in homework specifications, and especially in introductory courses like this one, you can count on the problem being completely specified, right? You can ask me questions. Is this what I'm supposed to do? Is that and I will tell you. Okay, I'll tell you exactly to the last level of detail what the specifications are. In the real world, okay, when you are a professional software engineer, a professional computer scientist, it's very rare that things are well specified. Very, very rare. So the problems are all kind of fuzzy, and it's up to actually us, computer scientists and software engineers, to actually make them more or less fuzzy, right? We need to figure out, exactly what the problem is. It's part of our job, figure out what the problem is. So, but that's not your problem here. In this course, you can rely, on me specifying everything to the last comma. But once you understand what the problem is, then you pass to the hard, sort of probably hardest part, which is how to solve it. Like, this is difficult, but again, it's very important that you understand what the problem is. Okay, understanding the problem is halfway to solving it. I can guarantee you. Actually, many times it's like 80% way to solving the problem. Okay, only when you understand something, it's so much easier to find the solution than when you don't understand something. So finding the solution, understanding how to solve it many times is about understanding the problem, right? So that's why there's a little sort of feedback loop over here. There's a feedback loop between understanding the problem and knowing how to solve it, because they really feed on each other. But anyway, so how to solve it? Here's sort of the general principles that a complex problem must be broken down into simpler problems. There's just no way that you can solve something that's complex like in one go. Okay, there's no way. You have to break it down. So that's sort of the very first basic principle. I'll talk more about this of computer scientists and computer science, is understanding that the first thing that you need to do, and the thing that you absolutely need to start with, the assumption is that you need to break things down, okay, and find out what are the little smaller parts that you can wrap your head around. And sometimes there are already existing solutions, so you don't need to solve it anymore. You just call the solution. For example, a typical example was, for example, you already knew how to read multiple inputs from the average program, right? So that part was already solved. You just had to reuse it, right, and kind of reappropriate it um, in the new program. So I'll talk more about this because this is really important. This is sort of the principles of how to reach solutions. But then there's a third problem, okay? We can have an idea for how to solve it. We can have, even write it down in bullet points. Okay, we need to do this, and then we need to do that, and then we need to do that. But then we actually need to express it in a language that is suitable for computers to understand, right? And unfortunately, computers don't understand bullet points, right? I wish they would, but they don't. So we have to transform our bullet points into something that's a little bit more formal and precise and unambiguous, okay? And that has a whole other set of challenges on its own that has absolutely nothing to do with algorithms, okay? It's a set of challenges that have to do with you being able to use some sort of a programming language effectively. So understanding what is it that the programming language lets you say, how do you map the pieces of the solution to that particular programming language? And then there's many programming languages, not just one. So that is a whole other set of can of worms here, and how to express the solution that is actually quite orthogonal to how to solve it. And there is some relation, but it's really how to solve it is one thing, and how to express the solution is another thing. And in many ways, when we talk about programming and computer science, these two things go together, and these three things go together, but they are really three different things. And it's important to know where in the process you are, okay? It's really important. So, for example, suppose that I tell you, build a Lego castle, all right? That's your task. Well, first thing is that you have to understand what castle you should build. What exactly, there are many castles. So maybe you want a castle with one tower, a castle with two towers. Does it have one door, two doors? What kind, is it on top of a mountain? There's all sorts of things that you may need to know, specify, understand what the problem is that you are being asked to solve, right? And so that the second level is once you kind of know what to build, then you have to devise how to build it. And that, you cannot just immediately start thinking about the bricks, right? that you don't go from understanding what you want to the bricks. You have to go through an intermediary stage, which is identifying sort of the major components of the castle. So maybe you want to focus on the tower. Okay, there's the tower. Maybe you want to focus on the gate. And why? Because all of these different components have their own challenges, implementation challenges. They're, the way that you think about building gates is not the same the way that you think about building the tower, for example, right? So they are fundamentally different components, and they may require different implementation. So you want to think about the components first. That's the part of really how to build it, the major, the bullet points of how to build the castle. You have to also bullet points the castle, right? And then once you have those components, then you really go down to the small bricks and devise how to express it in small bricks. That's where you go down to the level of expressing the design of the castle into whatever language you have. In this case, is the language of small bricks, right? So it's the same thing for many of you who played with Legos when you were kids. You probably know what I'm talking about. So it's the same thing here for algorithms. So let's again revisit the Max program again. Okay, now I want you to look at what I just did in the context of these three fundamental principles of solving computational problems, which is the what are you building, how to solve it, and how to express it. Okay, so these are the three different parts. So let's see. So in the Max revisit, you need to understand what the problem is, and in principle, when I had it specified, there were some things that were a little unclear, and some of you have asked questions in Piazza, right? That's great. That's part of understanding the problem. This is really great. If there's something that is not clear, at least in the context of an introductory course, you should definitely ask the instructor, what do you mean? Is this or that? Absolutely. For the upper division courses and later on in life, you'll see that unfortunately this is not true in general, but definitely for introductory courses, this is true. So the goal here was to find the maximum value on a sequence of up to 8 input numbers. And this is exactly the goal, okay? All words in here count. All of these words have meaning. Okay, find the maximum value on a sequence of up to 8 input numbers, okay? And an additional restriction is that if 0 input means that the sequence is over. So no more numbers. So these are sort of the requirements. But the requirements are kind of abstract, right? So one thing that helps a lot in understanding the problem is writing down concrete examples of input and output, right? So for example, if the input is this sequence of numbers, then the output should be 8, right? And if the input is this sequence of numbers, then the output should be 6. Means that, in the first case, you actually had 8 numbers. In the second case, you had only 5. The last one was a 0, so you just stop there. You stop accepting numbers, and you start, and you output the maximum at that point. So input-output examples are super important for wrapping your head around what's really being asked of you. Okay, it's super important. So that is my recommendation, my experience-based recommendation for how the very first part of the problem, solving computational problems, is trying to understand what you are being asked to do. And so how do you do that? Try to have concise definitions of specifications of what you are trying to do, but then also use examples of input-output. It really kind of gives you insight for what you are supposed to do. Okay, so then let's go to the second part, the how to do it. Okay, so now we understand that we need to do that, right? So now how are we going to do this, right? What is the computational process that is going to allow us to, given this input, you have this output, and given that input, you have that other output. Okay, again, this is very difficult. This part is very, very difficult, okay, in general. And it's one of those things that you get better with practice, but it's very difficult to get into it. So again, the strategy here is to break it down. Don't try to solve everything at the same time. So what you want to understand here is what's the possible simplest thing that I can solve here that is remotely similar to what I'm being asked to do, right? And there's no question in here, and then you add one constraint at a time. So for the max, if you think a little bit, then you probably would get maybe this is not there are many ways that you could start. Okay, this is not the only one. So for example, you could start with just accepting no more than 8 inputs. That would be a good place to start too, right? And at some point you figure out that you need to compare two numbers, right? You need to know how to compare two numbers and find out which one is greater. and you need to remember the maximum value of all the previous comparisons, right? So you have to remember this max number that applies to every time that you enter a new number. And so basically, start small, okay? Start with something very simple and then keep adding things to it. So if I do a decomposition like this, that I start by finding the maximum of two numbers, and then I add finding the maximum of many numbers, and I add solving no more than 8 inputs, and then I stop accepting zero. So having that I've done, these are my bullet points, right? You could have other bullet points, that's fine. The important thing is to have bullet points, okay? Having bullet points with small things at a time, this is very important. It's the most important step to being able to actually program, to being able to then represent this in a formal language. So start with your bullet points. It may not be exactly the ones that I have here, but there are some bullet points with smaller things that you need to do. So if these are my bullet points, now let's move on to how to express my solution into a formal language. Okay, now formal languages is a funny thing because there are many, okay, there's not just one. And there's something that you can do that help you go towards a more formal. So at the end, we need to write it down in some machine language. So for example, in the computing machine language that we have here. So that's our end goal. We have to write it down in that language. But it's not obvious that we have to go from these bullet points straight to that language. Okay, there's intermediary points that you can go. So I'm going to show you, this is called pseudocode. Okay, pseudocode is sort of a mixture of English with a little bit more of formal English, that it kind of helps you think of how to express this in a very completely formal, complete programming language like the one that you have in your computing machine. So, but again, you need to start small. And for your bullet points, whatever your bullet points are, so for example, this one, solve finding the maximum of two numbers. So this is, these are my bullet points for this task. Okay, this is how I solve this little task. Okay, this is not the machine code yet, but you can see how this is going to map to the machine code, right? So, we read one input, read the second input, then we test, and we update the max or not, and then, the maximum is in max. So you can see more or less this is going to be easier. This is how we're going, halfway to the machine language, how to express it in the machine language. Okay, so, and this would be then the other thing for, with one more thing that we need to do, solve the maximum of many numbers. And now you see that I'm starting my bullet points up here are starting to be a little bit more formal. There's a little bit of structure. There's, unusual things here. For example, the go to or go back to something, or, test. Like a test is an important concept. We need to test something, right? So there's a little bit of more formalities being in here on this box rather than on my bullet points. My bullet points are totally informal, just English. The things that I'm writing here inside this box are a little bit more formal, and etc. So what I have here is a sort of a semi-formal specification of the max, of how I would solve the max problem, right? So and it's not English, right? If you give this to somebody who's not a computer science, they say, what is, like, this is not English, proper English. No, it's not proper English. It's a pseudocode. So it's on the way to a formal programming language, but still enough English that a person could perhaps understand what is going on in here. So this is called pseudocode. All right, it's a very important intermediary representation between, once you find how to solve, once you have your bullets, right, your bullet points, the major parts of your solution, then write it down in pseudocode. All right, don't jump immediately into machine language because that may be too difficult. Okay, but so write it in pseudocode. And now once you have it in pseudocode, something like this, right? Something like this box over here. Now let's try to map this into our machine language, or whatever programming language you need to map, right? So identify the parts of the solution in pseudocode. And again, I would recommend starting with the smallest thing. That I'm a very big fan of incremental solutions, right? So you start small and you add more things, you weave more things, because if you try to do everything at the same time, chances are that everything breaks. You are incapable of keeping track of so many things. So start with the smallest thing that can work and weave in all the other parts. So let's start again with our smallest thing that I identified as my way of solving the problem, which is to compare two numbers, right? So this is compare two numbers. Let's go back again to the smallest thing that can work, the first bullet point. And now let's translate this from pseudocode to whatever programming language we need to translate. In this case, it's the machine language of these computing machines that I gave you. So read one input is read in, read another input is another read in. We put it in register 0 and register 1, and then we test, right? So we test if one is greater than the other. How do we test? Well, it's with there's subtract or divide or something. By the way, the machine now has more instructions, and I'll talk a little bit more about that. But in the beginning, it was like this: you subtract one from the other, and if the result is 0, then it's because R1 was bigger. So if R1 was bigger, meaning that the second one was bigger, then you need to apply the maximum, right? But now it's important. Okay, one thing that you need to realize is that when you have this in pseudocode, the semi-formal language, you will probably find yourself writing things or referring to things that are not inputs, but that are things that are important to have around. So for example, the max. The max, you need to remember the max. Max is a value that you need to remember from iteration to iteration. So what that means is that it means that you are going to have to store it in memory. Okay, you have to have a location in memory where you keep this max value. Okay, and in my office hour where some of you came, I was using location 15. Okay, so in location 15 is the place where I stored my current max all the time. So when you see 15 here, it refers to the current max. All right. So so in here it was the second input was greater, so then I have to update the max, which means that that's the store operation, right? It corresponds to this line, and then otherwise I don't do anything, and then I go fetch what's in the max, right? The max is here in memory 15, and I write it down. Okay, so this is my first bullet, right? The first bullet is just doing this. Just the important thing here is to realize that, oh, I need to keep track of this max. All right, I need to store it somewhere. And that's sort of the insight in here. And so for that, you need to be in this language, in this particular language, you need to be very organized and say, okay, write it down on a piece of paper on the side. Location 15 holds the maximum value at each point. Okay, this is something that you need to honor, you need to adhere. Okay, we are very organized. Don't mix up things with locations, otherwise it's a mess. So identify the pieces of information that need to be kept around. Maybe it's a max, maybe it's a counter. You need to identify what is it that you need to keep around, and then that means that you need to hold them in some location in memory. All right, and so then we solve this problem. Then we start weaving our other bullet points, right? So the other bullet point is to find the maximum of many numbers by remembering the last maximum number, right? So here's the black lines of code is what we had before, and in order to do that, we just need to add these blue lines, which are now in here. After we read the next number, we go and retrieve the maximum from its location, which is location 15, and then we compare. Now we compare the new number with the maximum that was stored in memory 15, right? This is how we compare it here. And then we do the same thing. We jump if it's 0, we jump to memory 7. Otherwise, we replace the maximum again. All right. And then we have this loop over here, jump 2, and this is the loop that never ends, right? So we need to fix this again with the other thing. Here are the reading 8 numbers, right? So it's only 8 numbers. That means that now we need this counter. Okay, this counter is something important that we need to hold on to. Means that there's another, probably, maybe you can hold it in one register. Okay, remember, we only have 3 registers. Sometimes what you do is such that you can hold on to something in a register, but sometimes you need all the registers and it doesn't fit there. You have to put it in memory. So in this particular case, I was able to do this by putting using R2, the R2 register as sort of the memory for the counter, and it's always there, and I never do anything with register 2 other than decrement it, okay? But in general, you would probably need another piece of memory to hold on to the counter and go, fetch it and store it whenever it's appropriate. But so these are the lines, the green lines that come from adding this accepting 8 inputs thing, right? So the decrement and stuff like that. See if you reach to 0, and if you reach to 0, then you get out of the loop. And then finally you put the other one, which is to test if the input is 0, and that is just with this little line over here that you test whether the input is 0, and if it's 0, just jump to the end. Okay, so in other words, what am I saying here? So start bulletizing. Okay, so in your solution, sometimes it's hard, but whatever it is, you need to bulletize it, right? So you make bullet points about what is it that you need to do, and then transform those bullet points into some sort of a semi-formal language, pseudocode. And when I say pseudocode, I'm not even. You'll find a lot of tutorials out there on YouTube that are actually treat pseudocode almost like code. Okay, as far as I can tell, what they're explaining is Python, and it doesn't need to be. Okay, something as simple as what I'm writing here is enough. Okay, something that has the concept of looping back, that has the concept of a test, right? So those are things that you need to express in this semi-formal language. So write it down in this sort of semi-formal pseudocode language, and then translate from that pseudocode language into instructions in your programming language that you need to solve the problem. That's basically what it is. Okay, and then weave again. Start small and weave in the things one at a time. That's usually a very good thing to do. So, fundamental principles for solving computational problems. First, you need to understand what you are solving. Okay, what's the problem? You need to devise how to solve it. And again, this can be difficult, but it helps that you understand what you are trying to solve. And in order to do that, the thing that you always need to remember is don't try to solve the entire problem at once. That is just way too complicated. You have to break it down. Break it down in smaller things. Write bullet points about what are the things that you need to do. And then how to express it? Well, you could perhaps go from the bullet points directly to a program, an executable program, but sometimes that can be very difficult. So what you may want to do is go from bullet points to pseudocode, and then go to pseudocode to an executable program. All right, that intermediary pseudocode sometimes helps you guide how the program is going to look like. Okay, so that's basically how you're going to, my half an hour explanation of how to create algorithms, algorithms, and it's hard. Okay, some algorithms are very hard, and there's, as I said, there's different kinds of difficulty. There's the inherent difficulty of figuring out how to solve it. So, for example, if I tell you, okay, write an algorithm that visits all the nodes of a graph, but it only visits each node once, right? So you have a graph where you have many nodes and edges. There can be cycles in the graph. But so if I tell you, find a graph traversal, called graph traversal algorithm, that only visits the nodes only once, not twice. It doesn't get stuck in circles, okay? So if you have to think about, how am I going to solve this, right? So that is a hard thing in itself. And it has nothing to do with the programming. We're writing it down in the programming language. Just thinking about how to solve it, what you need to do, the kinds of things that you need to remember, what have I visited this node before? What? So that is the puzzle solving. The puzzle solving part has nothing to do with actual writing the program for it. Okay, there's a first step of solving the puzzle. And then once you solve the puzzle, once you understand, aha, I have a solution for this, I solve the puzzle, you write those things down in bullet points, right? And then you transform it into some sort of a semi-formal specification, pseudocode, and then you go and write it down in some programming language. That's how it goes. All right, any questions about this part? Okay, so this is just a lecture about it. You will exercise it in the algorithms project, and so you can let me know how good or how bad. These things are hard. You kind of have to do it in order to understand. But I hope that at least I gave you a skeleton for how to wrap your head. If I tell you, find, write this program, at least you should know where to start. Okay, and remember that there are these three things: understand what the problem is, find the solution in bullet points kind of thing, and then write it down. There's three different things. And in fact, in the project, in algorithms project, there are different points for these different things. So there's points for writing the pseudocode, and there's points for writing the code, because it's really two different things. Okay, so having said that in general, let me move on to a part of which there will be more next week in the video lectures on Tuesday, which are famous algorithms in computer science. These are algorithms that every computer scientist knows. It's something that is so mundane that actually we don't even write them anymore, because there's already pre-packaged solutions that do all of this stuff for us. When you're a professional programmer, you don't even think anymore about sorting, because it's already, most programming languages already offer some function that is sorting the right way for whatever we want to do. But nevertheless, when we are learning computer science, it's super important to understand some of these algorithms, because this is the sort of the bread and butter of what programming is about. This is things that the computer, in our programs, whenever we have a computational task to do, we do this so often. These situations happen so often, and they need to be solved so efficiently that it's important to know what can we do, right? And this is not something that we need to reinvent. These algorithms have been around for many, many, many years, because they've been, as I said, people have been inventing these algorithms for the past 70 years. So those are now textbook algorithms. So I'm going to talk about sorting algorithms, and then a little bit about searching algorithms. Um, so for sorting algorithms, actually today I'm only going to talk about sorting. I have some video lectures about searching algorithms, and I'll talk about search on the next week on Thursday. And then besides sorting and searching, so that another very popular class of algorithms in computer science are graph and trees. So a lot of things have to do with trees, and I'll explain a little bit more. That tree, the tree data structure is something that have a node at the root, and then that node has many children up, and then each child has more children, and so there's sort of a tree-like structure. This happens to be a very useful data structure in computer science too, because it makes certain things very efficient. For example, search. Another one is graph algorithms. You have, for example, a bunch of cities or something that are connected with some cost function between the cities, and you need to find optimizations, like how do you go, for example, imagine Amazon, the Amazon delivery system. They need to optimize things, right? So they need to figure out what's the most optimum route to deliver a package from A to B, right? And they need to know, all that stuff is optimization algorithms over graphs. Basically, you have a graph, and now you need to find the most optimal route according to whatever criteria. So that's all stuff, the bread and butter of computer science. But so what I'm going to cover today is sorting algorithms. And what is the problem of sorting? So first we need to understand what the problem of sorting is. So what is sorting? Sorting is, given a set of numbers or whatever, strings or something, give a set of things that have something that is sortable, order them in ascending or descending order. So for the numbers. So for example, again, here are some inputs. If you have these inputs, 3, and we usually read this from left to right, 3, 6, 1, 5, 8, then the output should be 1, 3, 5, 6, 8. This is sorted. The same numbers, but are sorted. This one, the input 10, 8, 3, 5, 101, then the output should be 3, 5, 8, 10, 101. All right? And computer scientists have a very long list of sorting algorithms. You'd be surprised at how many algorithms for sorting there are. You may think, like, what? Is there not only one way of doing this? No, there are many ways of sorting, and each one of them has their own characteristics and their own advantages and disadvantages. It's quite amazing. Again, if you do this with a small number of numbers, like 5 here in this case, and you give this to a person, you give this to us, we do this in no time, okay? Like we don't even think. I mean, it's pretty obvious what the right order should be, right? We don't even need an algorithm. We humans do not need an algorithm to sort numbers, right? Our visual system is so powerful that very quickly we have a lot of parallel processing going on in our heads. Very quickly we know exactly which number should be where, and we don't even have sort of a rational a mechanism that we know or how to express. So in other words, even if you have no idea about what computer science is, if you have never heard about algorithms in your life, if I tell you, here's these numbers, sort them, you will be able to do that, right? Without applying any algorithm whatsoever, right? You just do it. But again, that's not how computers work. We have to tell them computers are completely dumb. They don't know anything. We have to tell them every single step. But again, the power of this is once we tell them, then they can go on it and they can do things that we cannot do. Like, for example, sorting a million numbers, right? If I give you, okay, sort a million numbers, you would say, okay, you're kidding me, right? That would be a very difficult task for us humans, but it's a completely trivial task for computers, right? Once we devise the steps for uh, sorting in 10 numbers, then it's exactly the same steps for sorting a million numbers. There's no difference, right? So it's great. So let me walk about around some famous sorting algorithms. So here's a list, not complete list of sorting algorithms, and they all have funny names. So there's the bubble sort, selection sort, insertion sort, merge sort, quick sort, counting sort, radix sort, heap sort, bucket sort. There's all sorts of sorting algorithms, all right? And you can see them in Wikipedia. And I have some links also that I will share with you that have very nice visualizations of what they are doing. So let me start with a selection sort. Um, so by the way, the simplest of all is bubble sort. So bubble sort is very simple algorithm, and it's the topic of your homework. So in your homework of algorithms, I'm asking you to, I actually already give you an implementation of bubble sort in the computing machine. You need to write down the pseudocode for it, and then you need to change that algorithm with a few more things that aren't quite right in it, and you need to fix it. All right. So that's bubble sort. So because bubble sort is the topic of your homework, I'm going to focus on selection sort. All right. So selection sort is does the following thing, and I have a visualization here. Hold on, let me go here. I have some blocks in here. All right, in world, that I'm going to show you how to do. So I have a bunch of blocks in here that are unsorted, as you can see, they're all over the place. So the goal here is that I want to have the longest ones on top. So I want to order so that the longest ones, so the second one is going to have to be on top, and then the last one is the second one. I'm already giving away the algorithm, right? So I want to sort them so that the longest one is on top and the shortest one is on the bottom. And so how am I going to do this? So first of all, let me, if I'm a computer and if I'm going to have to explain this to a computer, then what's happening is that these are going to be numbers somewhere, and they're going to be numbers in a piece of memory. So they're going to be numbers in memory. So an important thing about when you're doing these algorithms or thinking about algorithms is that you always have this concept of things being in memory locations. So for example, there's, besides the values themselves, so there's the memory locations and then there's the values in the memory locations. So for example, in this case, you have, the memory, and I'm going to sort of do it more or less like what we have in the computing machine, that memory location 0 is here on top, right? So this is memory location 0, and then this is memory location 2, I mean 1, and then this is 2, and then this is 3, and then this is 4. And then if you remember, in computer science, in most programming languages, the first position starts at index 0, not at index 1. This can be a little confusing. So this is memory location 0, 1, 2, 3, and 4, even though there are 5 blocks, right? So there are 5 blocks, and the indices go from 0 to 4. So now I'm going to do sort them, applying an algorithm that's called selection sort. So what is selection sort? Selection sort, the word selection means that I am going to select the maximum. So I'm going to select the maximum at every point, or the minimum. It could be the minimum or the maximum, doesn't matter. So in this case, I'm going to select the maximum every time. So I'm going to find out the maximum, and I'm going to put it exactly in its right place. So the maximum, basically, in selection sort, I say, okay, the maximum should be in location 0. The next to the maximum, the second maximum should be in location 1. The third maximum should be in location 2. The fourth maximum should be in location 3, and the fifth maximum should be in location 5. Right? That's what I'm going to do. So how am I going to do that? So I'm going to start at location 0, or it doesn't matter. You can start in either end of the spectrum. Doesn't matter. So let's say that I start here. And then I'm going to, remember, I'm looking for the maximum. So this is an algorithm that perhaps sounds familiar, because it is. So a lot of things that we do this all the time. So I'm looking for the maximum. So I'm going to apply some of these ideas that we already had in the maximum program. If I'm looking at the first one, then it's the maximum, right? Then, okay, so at this point, the maximum is location 0. Location 0 is the maximum. I'm going to put 0 here. 0. And then I move to the next one. And then have somebody blocking. All right. Then I compare the maximum that I have with this value over here. Okay, so it turns out that this value is bigger. Okay, so now the maximum is this one, at location 1. So I have to remember, the maximum is in location 1. All right, and I move on. Okay, is this bigger than the current maximum? No. Okay, move on. Is this bigger than the current maximum? No. Okay, move on. Is this bigger than the current maximum? No. Okay, great. We've done with the first sweep, and we came to the conclusion that the maximum is in location 1. Okay, so now what do we do? What do we do here? Well, we go and we're going to put this maximum in its right place, right? We're going to swap it. So we're going to go here, and I'm going to put this guy over here. I'll fix it in a bit. I'm going to switch these two guys, right? So I'm going to put the maximum here, and I just flipped whatever was there. I swapped it with the current position with the position of the maximum. All right. So we're done, but not quite done, right? We're done with the first sweep. We're not done yet. Now we need to do it again. All right. But now, instead of starting at location 0, because we don't have to start at location 0 anymore because it's already there in the right spot, we're going to start at location 1. So in the second time, instead of starting at 0, we start at 1, right? So we start at 1. And again, this is the current maximum, so it's at position 1. We move on. Is this bigger than the maximum? Yes. Okay, so now it's location 2. Location 2 has the maximum. Let's move on. Is this bigger than the maximum? No. Let's move on. Is this bigger than the maximum? Oh, yes, it is. Okay, so if this is bigger, then now the maximum is location 4. All right, so if this is maximum now, I'm reached the end of the numbers, then I need to swap it to the second position, right? So this is the maximum, and it belongs now in the second position. So I need to flip them around. This guy goes here. This guy goes here. All right, so there. We've swapped them. All right, so we're done with the second pass, but we're still not done. We have to do it again. And this time, we're going to start at location 2, because the first 2 are already sorted. They're already in the right positions. So let's start here. We start here. This is the current maximum. Okay, location number 2. We move. Is this greater than the current maximum? No. Let's move on. Is this greater? Also no. Okay, then great. Then that's because that guy was already in the right place. Great. We're not done yet. There's still one more sweep. And this time we're going to start here. All right, this is the current maximum at location 3. We move on. Is this bigger than the current maximum? Yes, it is. Okay, and we're done. So that means that we need to swap them. All right, let's swap them. All right, we go here and we swap them. All right, bang. We have sorted this stack of cubes, of shapes. All right, we're done. So this is selection, it's called selection sort. And the reason why it's called selection sort is because we sweep the numbers many times, and at each sweep we're looking for the maximum or the minimum. It will work either way, all right? Maximum or minimum work either way. We're looking for the maximum. And we know that at each iteration, we know exactly where that maximum needs to go. When we find it, we know where it needs to go. You know, the first time that we sweep, it needs to go to position 0. The second time that we sweep, it needs to go to position 1. The third time that we sweep, it needs to go to position 2, etc. So we know exactly where it should go, right? So those now, so I'm assuming that you kind of were able to understand how selection sort works. Now, this is one thing. This is one thing to understand how it works. The next thing is, how are we going to write it down? Okay, and you can see that these are two different problems. One is to understand the problem, and now you even can even understand the solution. I'm pretty sure that after the visualization that I did here, you understand what I did, right? You understand the solution. But now we need to write it down. It's not enough for us to understand. We need to write it down, and then we need to write it in such a way that the computer can execute it. Okay, that is a whole other different can of worms. Um, so how are we going to write it down? So let me, uh, I would like to write it down. Okay, I would like to show you how I write it down little by little, but I'm not sure I will have time to do that. So I'm going to show you the final result, unfortunately. I wanted to show you me, struggling to write the things one by one, but uh, if I do that, I don't have time to actually show you another one, which is bubble sort. So let me just show you sort of pseudocode. So here's how we go. We definitely need to have a counter because we need to know in which sweep we are. And the counter is important because the counter is going to tell us where we are going to put the maximum, the current maximum, right? So the counter also doubles as a location where we are going, basically the selection location, where are we going to put the maximum, okay? So we started the counter at 0, and then we find the maximum of the n minus counter blocks. So, right, so we start at position p equals 0, um, and okay, actually, you know what? This is an algorithm that does exactly the revert. It puts the maximum on the bottom, if I remember this correctly. It doesn't matter. It sorts them anyway. So let's see what the pseudocode does. Start at position 0. So this is the current maximum. So you have something here that's called max p, which is the maximum, the position of the maximum. Max p means the position of the maximum value. So the current position, the position of the maximum value is 0. That's where you start. Then you move to the next position, and now you test if, well, first you need to test whether you reach the end. And this is the part where it's kind of hard to give you the solution, up front pre-made, because there's a lot of things that have been woven here from simple things. So this test is here to find out whether you already reached the end of the sweep. And if you reach the end of the sweep, then you need to swap the maximum, to the right spot. So swap what's in the position of the maximum with what's in the position n minus 1 minus counter. And then you increment the counter and you go back to start again, right? Um, Right, and then you test. Right, and then you test. This is actually the important thing. Which is, this is the reason why I don't like to show you complete solutions, because complete solutions sometimes hide the important core thing. So the important core thing is actually this line that oh, you know what? I'm sorry. I'm looking at my slides and I was talking. You guys had no idea what I was talking about. Okay. So this is the pseudocode for selection sort, slightly different from what I just demonstrated you. But the important thing is that this test over here is the one that tests whether you found the maximum or not. So in the case of selection sort, if you find a new maximum, you're not going to swap it at that point. You're just going to remember where you found it. So you're going to remember where is the maximum, what position that maximum is. That's the only thing that you do, right? And that's very important. And then you go back and you move the position again, then you test if you reach the end, etc. So what are the important things in this pseudocode that you probably would need? Do I have a pen or something? Maybe does this work? So the things that you would need to highlight would be, for example, that you need to remember this counter. Okay, this is important. You also need to remember this max p, which is the position of the maximum, right? And so these are things that are very likely going to be things that you need to put in some memory locations that you have to come back to them many times, all right, and update them. So the counter and this max p is something that you probably will want to store in the memory location somewhere, all right. And so I leave it as an exercise now how to write this in the computing machine. In fact, one of the there's extra credit in the algorithms project. You can do any one of the other sorting algorithms, can be selection sort if you want, or insertion sort is also simple. So do the same thing that I did here, understand the problem, write it in pseudocode, and then write it in machine code. All right, so now I want to show you bubble sort. Bubble sort is the one that you have the code that I gave you the code. You need to write the pseudocode. So I'm not going to give you the pseudocode, but I'm going to show you how bubble sort works and how it's different from what I just did here with the selection sort. And and the reason why there are so many sorting algorithms. So let me go here and just show you bubble sort. And now I need to mix them all up again. Hold on, let me change their sizes all over again. Okay, so suppose that we have these blocks, and now we want to sort them. We want to sort them, but we want to sort them using bubble sort. All right, so bubble sort is going to do something slightly different. So bubble sort is we're going to make many sweeps. We're going to sweep the blocks many times. So we're going to start at the top, and then we're going to compare. We always compare where we are with the next one. So we're going to go, and I'm going to highlight this in different colors. So let me go here. I'm going to change the color of the ones that I'm comparing. So I'm comparing this one and this one. Okay, so I'm comparing these two. And then I say, okay, which one is bigger? Okay, so the second one is bigger, which means that we need to swap them. Okay, so we're going to swap them because the next one is bigger. For sure it should come before the first one. All right, so we're just going to swap them already. All right, so swap them. All right, good. So now we're done with this guy. So let's put them back to white. And now we're going to move. Okay, we did one swap. Now we're going to move. Now we're going to compare this one with the next one. All right, I'm going to put it in red. These are the ones that we're comparing. Again, we're finding, is the next one bigger? Yes, it is. Okay, if it's bigger, then just let's swap them. All right, great, let's swap them. Great. Okay, so we're done with that one. Let's put white over there. Let's move. Now we're going to compare this one with the next one. Is the next one bigger? Well, actually it is. Okay, so let's swap them again. Okay, good. Put them, move again, this guy, compare it with the next guy. Is the next guy bigger? Well, yes it is. Okay, we have to move them again. All right. Okay, and then we move it and we, wait, to put it red. Sorry, this was supposed to be yellow. This guy is supposed to be white. Okay, now we move it and we realize, okay, we reached the end of the numbers. So there's nothing else to swap right now. So let's go back again. Okay, so we move this guy, I'm sorry, keep changing the, okay, we move this guy to white and we go back again. Let's start at the top. Compare this one with the next one. All right, is the next one bigger? Yes, it is. Okay, then let's swap them already. All right, we swap them. we move this guy, move one. Let's compare this one with the next one. Is this one bigger? No, actually it's not. Okay, if it's not bigger, then let's move away to the next one. Let's compare this one with this one. Is the next one bigger? Yes, it is. Okay, then let's swap them. Okay, we've swapped them. We move. We're comparing this one with this one. Is this one bigger? No, it's not. Okay, if it's not bigger, then great. We don't swap them, and we move. And by the way, we reached the end of the number, so there's nothing else to compare. We put this, there's nothing to compare, we go back. Now we go back again, and we do the same thing. We do this one last time. So we could do this up to n times, right? Or at n minus 1 times. And those are the details that you need to study in the homework project. So we do it one more time. We compare this one with the next one. All right. And is this one bigger? No, it's not. So this one, there's nothing to swap. Let's move on. Okay, we compare this one with the next one. Is this one bigger? No, it's not. Okay, let's move on. We compare this one with the next one. Is this one bigger? No, it's not. All right, move on. This one with the next one. Is this one bigger? No, it's not. All right, move on. And we go here, we reach the end of the line. There's nothing else to compare. And at this point, at this point, you should realize that things are already ordered. And even if you didn't do 4 sweeps, which I'm not sure how many sweeps we did, in the worst case scenario, we would have to make 4 sweeps out of, or maybe 4 sweeps out of the data. But even if it may happen, the nature of the data, that after 1 or 2, the data gets sorted already. And in that case, you should not continue to sweep because you waste time, computational resources. So when you have to detect that the bricks are already ordered at some point. It may be the case that the bricks are already ordered, and you have to detect that and stop earlier when you detect that. So that's part of the homework. Okay, but the important thing, yes, Bevan, yes, I will tell a little bit how to do this. The important thing, before I explain how to do this in the computing machine, the important thing to notice the difference between selection sort that I showed you and bubble sort, if you remember, is that selection sort, we were selectively looking for the maximum at every sweep, right? And once we find the maximum, we knew exactly where to put it, right? In bubble sort, and the reason why it's called bubble is that the values bubble up or down. So the maximum bubbles up, and the high values bubble up, and the low values bubble down. It's at every point. You see them kind of swapping one by one, right? Whenever we can do local swaps, we do a local swap all the time instead of doing these big jumps. There's never big jumps in bubble sort. In bubble sort, there's only local jumps between the adjacent values. In selection sort, there are these big jumps between some maximum that's in some position and then goes to position 0 or 1 or whatever. Okay, so those are the differences. There are many more differences. If you read through, visit some of the sites that I have there for you to visit and see these illustrations, you'll see that there's all slightly different. And you may wonder, why would computer science obsess about this? Why do you need 10 different sorting algorithms instead of just one? Well, because they all have different performance characteristics, memory and runtime characteristics. So what does that mean? They all require different, some of them require that you remember more things than others. So for example, for selection sort, requires more memory than bubble sort. Bubble sort, you almost don't need to keep anything in memory. But and some other algorithms are much faster at sorting than others. So bubble sort is not necessarily the fastest sorting algorithm at all. There are much faster sorting algorithms than bubble sort, but bubble sort is definitely very simple, super simple. So you don't need a lot of memory, and things get sorted at the end. So that's bubble sort for you. So now let me talk a little bit about homework projects. Let me go here. By the way, if you go to this lecture that is linked from this, oh, again, I'm not showing what I think I am showing. Here. If you go to the lecture that is linked from the syllabus, today's lecture, there's a link to this really nice visualization site where you can play around with all of these different sorting algorithms. So for example, you can go here, say bubble sort, for example, 6, 3, 4, 1, 8, and then you run it, and then there's sort of a visualization here that you can run it, or you can run step by step to really understand what is going on. It tells you at every step what is going on in here, what's going on, starting at pass 0. So for each element, blah blah blah, compare the elements and this, etc. Okay, so you can see this visualization of the different it's very good for understanding the mechanics of the different sorting algorithms. Okay, but what I really wanted to show you is oh, I have it here already. So the project that you have to do, which is due not this Sunday but the Sunday after, Perla has a question. So let me answer the question first from Bevan. So Bevan is asking, for this code, are we going to incorporate the computing machine from the first project? Yes, we are. You're going to use the computing machine. It's a little upgraded, okay? I've added a few new instructions that are going to make your life so much easier. So, and some of them show up already here. So I give you, for example, this program that does bubble sort. And you'll see that there's already things here that didn't exist before. So one of them is like random 4. So random 4 fills the first 4 slots in memory with random numbers. Okay, this is convenient. If you're doing sorting algorithms, it's kind of annoying to always ask the user to input numbers. Okay, so you just put them, random 4 random numbers in memory, or whatever, n number of numbers in memory. And another thing that you'll see is this compare. Okay, this is a super useful thing. Instead of having to subtract or divide or whatever, and you had to look into the value of that register, you just have a compare or compare star. As usual, compare star means that you compare the locations referred to by values that are in the register. So you're comparing the values of location 2 and 3 in this case, right? And if you look at what compare does, it leaves something on register 0. If it's a 0, it's because R1 is bigger. If it's a 1, it's because R2 is bigger. I'm sorry, here. R2 is bigger. And if it's a 2, it's because they are equal. So you could actually test for equality if you needed. Okay, so read the specifications. I link it here. There's a list of instructions, and there's the specifications of what these instructions do. So there's increment and decrement. Okay, these are super convenient. Now you don't need to set 1 in some register just to add 1 to another register. Just say increment some register or decrement some register. This is super useful. And then there's this compare, okay, and the compare star, and then there's swap, again, super useful. Okay, you don't need to yourself to pass through the registers and copy one register with the other, whatever. You just have a swap, and it just swaps in memory magically for you. And then it has these randoms and fill up and fill down with that put numbers in memory. Okay, so that was Bevan's question about whether you're going to use the computing machine. Yes, we are. Make sure that you understand the new instructions that are available to you that are going to be super useful for sorting algorithms. And then Perla has a question, what is the Discord? So there is a Discord server. If somebody could just type it here on the chat, I will try to. So there is a Discord server here. Somebody also gave it here. Discord. Okay, there it is. So if you go to Piazza, you will see many references to the Discord server, which is a server that is run entirely by the students. I am not on it. I know that it's doing a really good job for organizing and coordinating the network project, so I would encourage everybody to sign up for this Discord server. Let me type it here and also type it here. Region details. Okay, there you go. Okay, so another question. Is there going to be a class or object activity you need to be. Oh, thank you. Yes. Okay. Oh my God, we're already 5 minutes past the hour. Okay, everybody, don't forget to check your attendance. And the object today is this beautiful armchair. All right, that's our on the stage. Please right click on it and then take a copy. And it's called the algorithms chair. And it's a chair that doesn't do anything other than you can sit on it and think hard about algorithms. Okay, that's the algorithms chair. And we have somebody already sitting on it. That's great. Getting ready for the homework. But what you need to do is to right click and more and take copy and then put it on your lawn. All right, so that's your algorithms chair right there. Okay, so I will see you in Piazza and in World and around, and I'm looking forward to see all your messages of the simulated internet going all around the world. Okay, bye everybody.